First law of thermodynamics, presented by me, Matthew Nelson. This is 5.2. Alright, the first law of thermodynamics was developed by James Prescott Joule in 1841, and it states that energy can be converted from one form to another, but it cannot be created or destroyed. This is important because he came up with the idea for the equation Q lost is equal to Q gained, where Q equals heat, so heat lost is equal to heat gained. When you begin to study thermodynamics, it's very important to understand the difference between a system and a surrounding. A system is a well-defined space used to keep track of energy as it undergoes change, and the surroundings are everything outside of the system that you don't want to track. It sounds a bit confusing, but basically a system is what you're measuring during a chemical reaction, and the surroundings are what you're not measuring, you're not keeping track of. Internal energy is the sum of all the kinetic and potential energies of the system. So in this closed system over here, it is all the energy that the particles hold. All right, change in internal energy equation. There's a few different ways you could solve for it, but this is the one we're going to look at first. It's internal energy final minus internal energy initial gives us the change in internal energy. And once you get that change in internal energy, you have to write that in following three different rules. One, it has to contain a number. This could be 1, 2, or 3. 2, a unit. This could be like joules or kilojoules. And then 3, a sign, either positive or negative. If your change in internal energy is missing one of these, it is wrong. All right, now time for you guys to try one. Or I'll lead you through this one, pardon. A system has an internal energy value of 560 joules. Then a chemical reaction takes place. Once the reaction is completed, the internal energy is measured once again with a reading of 990 joules. What is the change in internal energy? So there's not too much math that has to go on. It's mostly just picking out numbers. So we just have to figure out where to pick them out from. So the one that's going to be the initial is going to be the one that's measured first, and then the final is the one that's measured second. So we have to think about how it's written and conceptualize it. So we got 560 joules, then a chemical reaction takes place. That leads me to believe that this is the initial, and then this one obviously would have to be the final based on deduction, but you know it's not because it's measured once again, or you know it is because it's measured once again with a reading of 990 joules. So from this you could take the final 990 joules and subtract it from the initial 560 joules, and that'll leave you with 430 joules. Alright, now this one is for you guys to try this time. A system has an internal energy of 890 joules, then a chemical reaction takes place. Once the reaction is completed, the internal energy is measured once again with a reading of 430 joules. What is the change in internal energy? I'll give you guys a few seconds to complete it, but feel free to pause it. Alright, so the internal energy initial will be 890, and the internal energy final would be 430, leaving us with a negative value of 460 joules. And we know this because 890 was measured before the chemical reaction takes place, and 430 was measured after. Alright, and now we'll be learning about what the signs mean. So whether it's a positive or negative sign, we can conclude whether it's exothermic or endothermic. Whether it's negative, like the one you just did by yourself, that will be an endothermic reaction because of the negative sign value. It means that it's losing energy to the surroundings. Whereas if it's a positive, like the first one we did together, that's going to be exothermic because it's gaining energy from its surroundings. Alright, now let's relate the change in internal energy to heat and work. Change in internal energy is also the sum of heat and work, where heat is equal to Q and work is W. Q could either be positive or negative depending upon the heat is being added or taken away, and whether work is being done or on the system. Alright, now I'll walk you through a heat and work equation. Alright, gases A and B are combined in a cylinder and piston arrangement. Gas A plus gas B will give us a solid precipitate. As the reaction occurs, the system loses 1,150 joules of heat to the surroundings. The piston moves downward as the gases react to form a solid, as the volume of the gas decreases under the constant pressure of the atmosphere. The surroundings do 480 joules of work on the system. What is the change in the internal energy of the system? Alright, so what we're going to be picking out here is we're looking for Q and we're looking for W. We know that loses 1,150 joules of heat, so that's going to be the heat. And then we know 480 joules of work, so that's going to be the work. Now we just have to figure out the signs, and since it's loses, that's going to be negative, and since the surroundings do the work, that's going to be positive. Another thing to note is what I've underlined here, and that just signifies that it's under constant pressure of the atmosphere. So there's no strange variables that we'd have to factor in. Alright, so now we've got the negative heat at negative 1,150 and the positive work at 480 joules. You add them both together and you get negative 670 joules. Alright, now for you guys to do on your own. Calculate the change in the internal energy for a process in which a system absorbs 140 joules of heat from the surroundings and does 85 joules of work on the surroundings. I'll give you guys a couple seconds to complete it, but feel free to pause it and take as much time as you need. Alright, here's the answer. Q is positive and W is negative because of the surroundings doing the work. Because the system absorbs 140 joules, that's going to be positive, and because the surroundings do 85, and the system does 85 joules of work on the surroundings, it's going to be negative. So that's 140 plus negative 85, which will give us 55 joules. Alright, now let's take a look at state functions. These are a little confusing when you start to learn about them, but start to make more sense as you get further. State functions are properties of a system that are determined by specifying the system's conditions. So they're basically just a set point, like it doesn't matter how they got there, only that it's there currently. For example, if you were to have 2 glasses of water on a table, it doesn't matter where they were yesterday. One could have been frozen, the other one could have been boiling. All that matters is that they're both room temperature water. That's it. Just like the water, it's a state function. Heat is a state function. Alright, this has been understanding and applying the first laws of thermodynamics. Thank you.